So let me tell you what a tree is. A connected undirected graph with no simple circuit. So a tree is nothing but a connected undirected graph with no simple circuit. So here I have a graph. Is this a tree? Is it satisfying the definition? First of all, is it connected? Okay. Now, is it having any simple circuit? No, there is no any simple circuit, right? So it satisfies this definition. All right. Therefore, this is an example of a tree. All right. So now I'll give you some graphs. Tell me whether they are trees or not. You look at the graph G1. Is it a tree? First of all, it is connected. Therefore, no issue. And next, does it have any simple circuit? No. So therefore, can we conclude this is a tree? This is an example of a tree. So the graph G1 represents a tree. So how about Z2? Is it a tree? No. Why? Which property failed to satisfy? It is not connected. Yes. So you can see that the graph is not connected. Suppose if I draw it separately, suppose if I take this vertex down, let's say here, right? Then the graph looks like this. Okay, now it is not connected graph. It is not a connected graph. So if it is connected graph, then we will verify whether does it have a circuit or not. So since it is not connected, okay, I don't verify further. So it cannot be a tree. All right. So this is not a tree. Yeah. So how about D3? Is it a tree? Yes. Okay. So this is a tree, and because it is connected and you're not finding any circuit in it, any simple circuit in it. How about G4? Yeah, G4 is not a tree. What is the reason? What is the reason? It has a circuit, yes. So you can find a circuit here, but tree cannot have a circuit. So therefore, this is not a tree. And how about G5? Is it a tree? Yes. G5 is a tree because it is connected and there is no simple circuit in it. All right. So I hope you can identify whether a given graph is a tree or not. All right. So how about this? Yeah, this is also an example of a tree. Say something about trees here. See, if a graph is a tree, then definitely you're not allowed to have a multiple edges between the vertices. Yes or no? For example, if you have a multiple edge, let's assume that this has a multiple edge here. Then what happens? Then this becomes a circuit, no? So this becomes a simple circuit. So it is not allowed to have a multiple edge, and also this is a tree is not allowed to have a loop, because if you have a loop, that itself is a circuit. Okay, so loop can be considered as a circuit. So we are not allowed to have loops or multiple edges in a tree. So this says that between any two vertices, uh, not between any two. Okay, if there is edge between any two vertices, that must be unique. Okay, you cannot have more than one edge, and there is no simple circuit. Okay, so if there is no simple circuit in it, now how many paths can you have from one point to another point in this graph? For example, I would like to start at this point V1. I'd like to reach this point V2. So how many simple paths we have? I hope max you can have is a simple path. You cannot have more than one path. So that is nothing but initially you can travel along this edge, and next you'll go to this edge, and finally you reach V2. Okay, so from V1 to any other vertex in this graph, we can have a unique path. Okay, if you want to move to V2, this is the only way you are allowed to move. Okay, you cannot find any other way. For example, from V1, if you want to move to V3, what is it? I'm talking about simple paths. This way only you can move. You may say something. You may say that, sir, from V1 to this point, let me name it as V3. You'll go like this and go like this and coming back and then reaching to V3. If I say just a path, you can have a path where you can repeat the edges. That is different. But I'm talking about simple path. When it comes to a simple path from one vertex to any vertex, that is unique. Okay, so that's what we can see it as a theorem. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. Right? So you take any two vertices of the tree, we can find unique simple path. Suppose if you find more than one simple path between 2 points, then that cannot be a tree. Okay, that graph cannot be a tree. All right. Now let us see what a rooted tree is. Okay, so what we are going to do is we are going to fix one point. For example, when you speak about family, it's like you may take one person and their children's and their children's, like that you can talk of it, right? A family of a person, maybe your father or grandfather, or okay, you may take your grandfathers, and you can see their family, right? So the root what you are taking here is your grandfather's grandfather. That is the root you are taking, right? Based on that, you can explain your family, like the children of your grandfather's father, all right, and then their children and all. Okay, so the terminology we use in family, that we are going to assign it to graphs here. Okay, so first let me define what a rooted graph is. Okay, let's assume that initially you have some graph like this. Okay, this is some random graph I'm taking. So now what I'll do is I'll pick up one of these vertex. Okay, so here I'm taking A. So I'm taking the vertex A and keeping this initially, and the edges which are adjoined, I mean the vertices which are adjoined to it, I will write it down like this. Okay, so initially I'm taking A on top, and next down to it, the vertex adjacent to B. Adjacent to A, which are B and C. Okay, that I have written. And next, you look at C, the vertices which are adjacent to C are D and E. Okay, and among D and E, E has adjacent vertices that I have written. Okay, so now this is a tree, and we call this is a rooted tree which is rooted at the point A. Okay, so this tree is rooted at E, the vertex A. See, for the same graph, you can have one more rooted tree. For example, I'm saying that A is not the root here, C is the root. So in that case, what do? You take C first initially, and the vertices adjoined to C here there are three vertices, D, A, E. Okay, so that you write it here, D, A, E. So these are the vertices which are adjoined to C. Okay, now you look at these 3 points, that is A, D, C. D is a pendant vertex, therefore it is not having any adjacent vertices, right? Fine. So how about A? Yeah, A is having one vertex adjacent to it, therefore, so that I will draw it down to it. And next, E has 2, that is G and F. G and F, I'll take it here. Okay, so let me name this. This is, oh, what is this? B and G, F. So this is the tree rooted at C. So here we are taking C as a root. Now suppose if you start E as a root, how the graph looks like. So this is the given graph. Now you are asked to draw a graph rooting at E. Alright, let me try to draw that. So initially I take E, and how many vertices are incident with E? Edges are incident with E. I have 1, 2, 3. So let me name it. So initially I am taking E, and then I am taking C, G, and F. Alright. And next, G and F are pendant vertices, so therefore no issue. So let me establish the connections. Next, C has how many connections? It has 3, isn't it? Because adjacent vertices here are D, A, E is already taken care, so no need of drawing it. So except E, there are only 2. So one is A, other one is D. Okay, I hope we got all. So now this is the tree rooted at the vertex E. Okay, so a rooted tree is a tree in which one vertex is designated as the root and every edge is directed away from the root. So but we will direct it down. It's like this, in the down direction. We don't mention the direction here, but you must understand it like this. Now let us see some terminologies in the graph. Okay, so now you take a rooted tree. So you know that this is a root. So no need to mention it again. So for this graph is rooted at a vertex A. Alright. So now I would like to speak about the vertices of the graph in terms of the vertex V. Okay, so I'm concentrating on the vertex V. In terms of V, I would like to speak about the other people. Okay, I'm going to speak about the relations now. Now if you take C, now this we are going to call this C, which is a parent of the vertex V. Okay, so this C can be taken as parent of V. Alright, now in terms of C, I can call this V, this is a child, V is a child of C. Alright, now who are the childs of V? The childs of V are given here, which are P and Q. So Q is a child of V and P is also a child of V. Okay, now what is W to V? So W and V are having the same parent. Okay, so now we call these two are siblings. Like W is a sibling of V. So W is a sibling of V. Alright. And next, how about the edges which are above V? Not the edges, vertices which are above V. Okay, for example, V parent and parent parent. Actually, this root is a parent of parent. I mean, V parent is C and its parent is A. Okay, so now we are going to call this A and C as ancestors of V. Okay, in Telugu we may say Purvikulu, right? Suppose if you have many connections, say for example, if I take R, if I take R here, who are the ancestors of R? So the ancestors of R will be P, V, C, A. Okay, so these are the ancestors of R we will take. Alright, so I hope you understand what a parent of a vertex and childs of a vertex, okay, and sibling of a vertex and ancestors of a vertex. Okay, now let me define one more thing. Now the descendants of V are nothing but the vertices which are down to V. I mean the children's and all. These are all descendants of V. Okay, that is P, Q, R, S. These are all will come under descendants of V. Alright, I hope given a rooted graph like this, you can identify parent of a given vertex, children of a given vertex, and siblings of a given vertex, and descendants of a given vertex. Alright, now let us define leaves in a tree. Okay, so leaf is the one, I mean, you can have only that one, right? The leaf, nothing is going to be connected to it. If you take a branch, it will have leaves, but if you take leaf, it alone will be there, right? So in our graphs, we call pendant vertex as leaves. Whereas in this language, the language that we define right now, the children, parents and all, okay, a vertex which doesn't have children is called a leaf. In other words, we can define it as a pendant vertex is called a leaf. So take a tree, in that pendant vertex is called leaf. The vertices which are not pendant vertices are the vertices that have children in the tree graph, which are called internal vertices. Okay, so let me give an example of a graph. Tell me what are internal vertices and what are leaves. So let me name these vertices as A, B, C, D, E, F, right? So what are leaves in this vertex? Is it just D, E, F? Is it just B? I am talking about all leaves. So the all leaves are B, D, E, F. Simply look at the pendant vertices. Pendant vertices are nothing but leaves. Alright. So what are the internal vertices here? Yeah, the internal vertex is C. If you include A also fine. But except the root we take while drawing the graph. So here the leaves are B, D, E, F. Right? Now the internal vertex is C only. And we don't consider A as an internal vertex. Root will not be considered as internal vertex unless root is only the point vertex in the tree. Okay. So now let me define a subtree of a tree. So for that, let me pick one example. So now I'd like to see a subtree which is rooted at C. Okay, a subtree rooted at C. So what is that subtree? Now you are going to take C as a root. Alright, so this C you are going to take it as a root, and rest of the vertices you will take it. Alright, so this is a subtree of a given tree, subtree rooted at C is this, that is C, D, E, F. Okay, similarly, what is a subtree rooted at E? So you can have only this, right? So this is the subtree rooted at E. Now let us define what is M array and full M array. So for that I'd like to take an example. So let me take this example. Okay, so now you tell me, if you look at each vertex, how many maximum children it has? You take the internal vertices including the root. Okay, so the maximum number of children here are 3 because C has 3 and E has 2 and A has 1. Right. Now let me write one more example. So let me draw it. So let us look at this graph. Now what is the answer to the previous question? The question is, how many number of children each internal vertex has? Maximum children, including the root. So including the root, there are 3, right? Okay, suppose if I name these vertices as A, B, C, D, E, F, G, H. The children's, I mean the pendant vertices, I'm not naming it anyway, right? So if you see that A has 3 children and B 1 and C 2, and when it comes to, oh, this is E, I think so. This is E. So C has 0 and E has 2 and D has 3, and similarly F has 1, G has 1 and H has 3. Okay. So now we are going to call this graph as M array, that is 3 array. Okay, so this graph is 3 array tree. I hope you must have understand what do you mean by 3 array tree. Every internal vertex has no more than 3 children. Okay, similarly we can define an M array tree. So here you can see the definition. A rooted tree is called M array tree if every internal vertex has no more than M children. Suppose, okay, let me, here also let me put one example. So here this is an example of 2 array tree. Okay, now let us see what is full M array tree. Now it means that every internal vertex has exactly M children. Like the graph you draw it in Stalin movie. What is it in Stalin movie? You take the initial person, he will help it to 3, and these 3 needs to help to the remaining 3. Yeah. So now if you look at that graph is going to be full 3 array tree. For example, yeah. So let me draw it. So this is an example of a 3 array tree, right? If you want, you can extend it. Alright, I hope you understand what is an M array tree and full M array tree. And we can define a binary tree. A binary tree is nothing but 2 array tree. Okay. For example, you can look at an example of a binary tree. Okay, so this is an example of a binary tree. Of course, here also you can have things like this. I'm just drawing few. Okay, it's not needed that you need to stop here exactly. So now I need to define, yeah, what is an ordered root of, ordered root tree. Okay, it is just to drawing the graph in a nice manner so that whether you draw or I draw, we will get the same graph. Okay, it is like this. You have a person and you take their children. You're going to write the first person here and the second person here. Okay, for second one, let's assume that he has 2 children and you write first here, second here. Similarly here you write it in this manner. Okay, we write it from left to right. Okay, so now ordered tree is nothing but children of each internal vertex are ordered. So how they are ordered? In general, we order it from left to right. So now let me consider this graph and let me assign name to the vertices. So the vertices here are let's say A, B, C, D, E, F, G. These are the vertices. Now I'm going to call this B, which is a left child of A. Okay, and this C is called right child of A. So in the graph we can understand like whether he is on the left side or right side. That's what. Okay. So such a graph we call an ordered graph. So an ordered graph, it means that it is not enough to give a rooted vertex and parent vertices and all. We must know the order from left to right. It's like which one is bigger and which one is smaller. Like that we need to know. It must be said who is left child and who is right child. Okay, so if we want to draw an ordered graph. Alright, now I'd like to define a level of a vertex. So it is there in the name itself, level of a vertex. So now let us do one thing, just for understanding. Yeah, I hope you can look at this graph. You see, the root I colored white, and the childrens of root I colored red, and the childrens of these red color vertices I colored with blue. Okay, now these blue colors one are at level 2. I say that these blue color one are at level 2, whereas the red color ones are at level 1. Okay, so these are level 1 vertices and these are level 2 vertices. So if you look at the level of B, that is nothing but length of the path from B to the root. So what is the length of the path from B to root? That is 2, because it is enough to cross 2 edges. Okay, so it is of path length 2. Therefore, we call the level of B is 2 and the level of A is 1. So now here I have a graph. You tell me what is level of this yellow color guy. What is its level? Yeah, it is 1. Someone is saying 2. Why is it 2? It's not 2. You see length of the path from root. What is root here? Yeah, that is 1. It's not 2. Okay. So how about level of this red color vertex? So what is its level? Some are saying 2 and some are saying 3. You see path length. Okay, how many edges you need to cross? 1, 2. That's it. So that you can move to the root. Okay, so it is at level 2. So the level of the vertex is 2 here. Right. Similarly, how about level of the vertex which is given here? Blue color one. This one. So its level is, yeah, this is also 2 because it's enough to cross 2 edges. Okay, now green color one, I hope you can see it here. What is its level? So how many edges you need to travel? 1, 2, 3, 4. So we need to travel a path of length 4. So therefore it is at level 4. Okay. Now let us define what a balanced tree is. Okay, before that I'd like to define height of the tree, height of a rooted tree. So height of the rooted tree is nothing but the length from the maximum length from root to any vertex. Not any vertex. You take the length from a root to any vertex. You take the maximum length. So the maximum length will be taken as height of the rooted tree. Okay, for example, when it comes to this rooted tree, what is its height? Yeah, that is 4. Okay, so let me show you the definition of height of a rooted tree. We can see that The height of a rooted tree is the maximum of the levels of vertices. So you take maximum of all the levels, so that is going to be the height. Or in other words, the length of the longest path from a root to any vertex. So that is how you can define height of a tree. Okay, so therefore the height of this tree is equal to 4. Okay, now I'd like to define what a balanced tree is. First I'll draw the picture. I hope you can easily understand. Now look at this picture. Is it balanced? I didn't give you the definition of balanced graph, but still I'm asking you. In general language, let us speak. Like if you keep it on the table, like does it stays or not? Simply like that. Can it stand? I hope it can stand like this. No? If you say no, what should I say? Right subtree is not balanced. Right subtree is not balanced. Okay, so the right subtree, it means this is what you're talking about. Why is it not balanced? Okay, first let me define what a balanced graph is. Later we will talk about it. So this is the definition of a balanced graph. We say a graph is balanced if all its leaves are at level h or h minus 1. Okay, you take a graph, you take a rooted M array tree of height h. So the tree height is h. Okay, so now you look at all leaves of the graph. So all leaves of the graph must be either at height h or at height h minus 1. So if they are at height h or height h minus 1, then we can say that it is a balanced graph. Okay, now I'll give you an example. Tell me whether that is a balanced graph or not. So is it a balanced graph? Yeah, because you can see that you can see the leaves, how many leaves it has. So let me mark the leaves with green color. Okay, so these are the leaves, and it is a tree of height 2, and these two leaves are at level 2 and this is at level 1. Okay, so this is at level h and this is at level h minus 1. Okay, it is satisfying this definition, therefore it is a balanced tree. Okay, so this tree is balanced. Now how about this tree? Is it a balanced tree? Now what do you think of the right subgraph? So is it balanced or not balanced? Yeah, right. Anyway, this is a rooted M array tree only. I'm not talking about full M array tree. It is not a full M array tree. Okay. So moreover, I can see it as a binary tree. Only thing, this has only one children. It is not having two children. So it is two array tree, and it is balanced also because all leaves are at level 3, and the height of the tree is 3. All leaves are at level 3. So now I'll give you an example. I don't say it is an example. And just taking one graph. Is it a balanced graph or not? No. Why? What is the reason? So what is the height of the graph first of all? What is its height? So height of the graph is 1, 2, 3, 4. Yeah, 4. Okay. So how about pendant vertices or the leaves? Leaves are located at, for example, the J leaf that is located at height level 1. Okay, and there is a leaf at level 2, and there is another leaf at level, so this is at level 1, this is at level 2, and where else the leaves are? This is at level 3 and this is at level 4. Okay, not all leaves are staying either at height 4 or 3. Okay, there are also leaves which are available at level 1 and 2. Therefore, this is not a balanced graph. It's very clear that this is not a balanced graph. All right. Now, so the question is to find the height of the tree. Okay, so you already know height of the tree. I hope you can write level of each vertex. So when you are asked to write the level of each vertex, this is how you need to write. So you create a table like this, a vertex. So for root level is 0 anyway, and you write the vertices which are at level 1, 2, 3, 4. Okay, so this is how you need to answer the question. So now you can pick up maximum among these. The maximum level is 4, therefore height is 4. Yeah, how about these trees? Are they balanced? Do you find any balanced tree here? So let me name this graph as G, G1, and this graph G2, and this is G3. G2, G3. Yeah, G2 is balanced, fine. How about G3? All leaves are at the same level. Yeah. So therefore 2 and 3 are balanced. But when it comes to 1, it is not balanced. Yeah. Right. The G1, it actually looks like a walking man in animation. Yeah. All right. So if you take a tree, how many vertices or how many edges it has? If it has n vertices, and I'm showing you the answer and I'm asking the question, and you wish that exam must be like this. Ah. All right. So how many vertices? Sorry, if a tree has n vertices, how many edges can we expect? For example, if it has only one vertex, it means there is no edge. Fine, 0. If it has 2 vertices, then we can have maximum 1 edge between them. Whereas if you have 3 vertices, then 2 edges. Alright, why? Because between any 2 vertices, maximum we can have 1 edge. Alright, so like this you can easily count that if you have a tree with n vertices, right, there must be n minus 1 edges. Suppose you take, this is a tree with 3 vertices. Alright, now you can see the number of edges, these are 2. But however, the drawings can be different. For example, a tree with 3 vertices, either it can be drawn like this, like having 2 children, or it can be drawn like this also. So however you draw it, you'll have, if you have 3 vertices, there will be only 2 edges. And let us look at some theorems here. Let me take an example. So from example, I will discuss. Okay. So you look at this graph. All right. So how many number of vertices it has? So number of vertices equal to how many are there? So here you tell me one thing, number of vertices and number of what is it we define? Internal vertices. And next thing, number of leaves. So how many number of vertices it has? Okay, 14. And how many number of internal vertices it has? Only thing root and pendant vertices you remove. Like you remove the root and pendant vertices. So out of 14, we have out of 14, how many we need to remove? I is also not internal vertex. 1, 2, 3, 4, 5, 6, 7 I need to remove. So I'm getting 7. Oh, E I need to count. Alright, then 6 only. So we have 6 internal vertices. Alright. So number of internal vertices are 6 and the total number of vertices are 14. Now do we have any relation between them? First of all, what kind of a tree is it? Okay, so this is a 3-array tree. But it is not a full 3-array tree. If it is full 3-array tree, we can tell about the relation between the number of vertices and number of internal vertices. Okay, why? Because knowing that internal vertices, and we can know how many children it can have exactly. Okay, so based on that we can easily count. So this is not a full 3-array tree. Okay, so we are not talking about these things. So we need to talk about a full M-array tree. So let's assume that there are M internal vertices. Okay, there are M internal vertices, and you may get confused. M array, it means I'm taking M. This is about number of childrens each one can have. So okay, I should not take M here. So let me take I. I represents number of internal vertices. Okay. So now, if you take each internal vertex, how many children it can have? It can have M number of children in a full M array tree. Now we are not going to consider the root as an internal vertex, no? Alright, so now I will include root in it. So this many number of total vertices we can have. So that is n equal to m into I plus 1. Alright, so that is what this theorem is about. A full M array tree with I internal vertices contains mi plus 1 vertices. Okay, so this one is a base. So let me take a binary tree. So you take this binary tree. So how many internal vertices are here? You can see that the number of internal vertices here are 1, 2, 3. So there are 3 internal vertices, and this is actually a full binary tree. Alright, so it means m equal to 2 here. So the total number of vertices are going to be 3 into 2 plus a root. So that's going to be 7. Alright, total 7 vertices it has. Alright, so let us look at one more theorem on full M array tree. So let's take n as number of vertices, and this I, or you start with a M array tree. Moreover, it is full M array tree. There is a lot of difference between M array tree and full M array tree. Okay, so if you take full M array tree, we can say that the number of internal vertices here are nothing but, what is it? We know the relation. The relation is n equal to mi plus 1. Okay, so therefore I will be equal to n minus 1 by n. So this many internal vertices we will have, and now the question is how many number of leaves it has. So number of leaves, how many are there? That is the question. Let me represent the number of leaves with the letter L. Okay, so what is your answer? So we can easily see that total number of vertices will be equal to the number of leaves plus internal vertices. But I hope we need to include one more thing, no? Here I listed it differently. This plus one is representing rooted vertex only, but the thing is, the rooted vertex is not a child of anyone. Here we are counting the number of children only. Okay, so this is counting the number of children's, but the rooted vertex is not a child of anyone, so that's why we are adding it at +1. Okay, so here the internal vertex is also, sorry, the rooted vertex is also considered as internal vertex. All right. So including the rooted vertex, we have I number of internal vertices. Okay, this I is including rooted vertex. And when it comes to L, this represents the number of leaves. So the number of leaves plus I will be equal to N. All right. So we would like to find L here. Okay. So L is nothing but N minus I. Now, how do you write this I? We already wrote it here. This is N minus of what is it? N minus 1 divided by N. Okay. So take LCM. So if you take LCM and simplify this, so this will be equal to Mn minus N plus 1 by M. So finally, taking N out, M minus 1 plus 1 divided by M. Okay, so that is what this theorem says. A full M array tree with N vertices has N minus 1 by M internal vertices and this many number of leaves. Okay, M minus 1 into M plus 1 by M, number of leaves it has. Alright. So as a corollary to the previous theorem, you can directly write this. A full M array tree with I internal vertices have Mi plus 1 number of vertices and the number of leaves are M minus 1 into I plus 1. And how do you get this formula? Because we have already seen what is the relation between L and I. L and I is equal to N. Now this implies L equal to N minus I, and you write this N in terms of this, that is Mi plus 1 minus I, and you can rewrite it like this, M minus 1 into I plus 1. So that's it. Directly you can write L equal to M minus 1 into I plus 1. Okay, so similarly the second condition you can obtain. Like finding total number of vertices, knowing it is a full M array tree and the number of leaves. Okay, and here deriving the number of leaves by knowing the number of internal vertices. That's what. Alright, so there is one more theorem which illustrates that there are at most M power h leaves in any M array tree of height h.